So I'm working on this Sansui 771 and just sitting here working on the things, and I've got a lot of time to think. I was thinking about these caps, what we use for replacement caps, and how they compare with each other. So I thought, why not try this? I got 4 caps here. They're all identical in value and voltage. 220 microfarad at 50 volts. I have a LKM. This is from Wyman. This is my go-to cap. This is I can't remember, 7 or 10,000 hour life at 150 degrees Celsius. I got a solid polymer cap, and this is from Honor Electronics, and these have a 105C rating, and they're rated at about 2,000 hours. I have a Chemet. This is your DigiKey Special, 220 at 50 volts. This is a 105C. This is probably the oldest cap in my stock here, because this one's got a date code of 1220. I think that's a date code. And this is just a standard cap, nothing special about it. And then I have a Nichicon Audio KA, and this is another 105C. Date code of 22, it looks like. So I got 3 caps here. How do they stack up and how do they perform? Like, what's the difference between these caps? They're all the same value and they're all the same voltage. So let's do some tests. Let's test capacitance, ESR, leakage current at full rated voltage, and then we'll check the ESR after we do the burn-in test with the full rated voltage. Let's see how these compare. Alright, so I decided to add another capacitor to the mix. This is a 50-year-old, I think it's 50 years old. There's no real date code on it. It's an Elna, removed from the circuit. See, it's been used. It's the end of its life. So let's check some of these caps here. So we got the Wyman. Let's go with this one first. Let's see what we get on the meter. I'm going to do this at 120 hertz to start, and then I'll redo this tests at a higher frequency. So our Wyman is at 200 microfarad, and it has an ESR of 244. And our dissipation factor, let's see if we can read that. 0.037. Let's do the solid polymer. And what does this measure? 216. And our ESR is 115 milliohms. And what's our dissipation factor? 0.18. Okay, now comes the garden variety here. This is, I checked the data sheet on this Chemet cap. It's just a regular general purpose cap, 105C. It's got a 1,000 hour life at 105C. So let's check and see what this one says. 192, and then we got 320 milliohms. Our dissipation factor will probably be a little bit higher. Oops, went right by it. So we got 0.46. 0.046. And our Nichicon audio grade cap. Let's try this one. Use 23 microfarad, and we got a 290 milliohms, 296, whatever. Dissipation factor 0.49, 0.049. Now for the use cap. Let's see what kind of stuff is going on here. Okay, we got 234. And we got a 168 milliohms ESR. And our dissipation factor, 0.29. That cap's holding up pretty good. Alright, so now what I'm going to do is I'm going to put these all on my leakage tester. And I'm going to put them on, and I'm going to raise it to maximum rated voltage. My plan is to leave it on because you can't just connect it up to a leakage tester and test leakage. You have to, these are brand new caps, they have to be allowed to form under the voltage that they'll be working on. So my plan is to connect it to the voltage and let it sit there and form for about 10 minutes. I'm going to make it 10-minute limit, and I don't want to be doing this forever. So I'll do each cap for 10 minutes, and then we'll take our measurement at the end of those 10 minutes, and we'll see what the measurements are. Okay, this is the piece I'm going to be using for doing leakage. It places a voltage across the cap, and it measures the current flowing through it. So turn this on, and it's set for 50 volts. Let's connect our first cap, which is the Wyman, and let's power this up. Okay. We'll turn up the current. Remember, these are brand new caps. So I'm going to let this go for 10 minutes, setting the timer, and we're going to see how much this leakage current comes down. After 10 minutes, we're going to take a measurement. We're at 200 milliamps right now, dropping to 100. Let's turn it up one more range, and we're at 70 milliamps and dropping. Okay, so this is the Wyman cap connected across 50 volts. This is the leakage current after 10 minutes. We are down right around, well, it's actually fluctuating between about 1 and 4 microamps. You can see the meters going up and down slightly as it forms little bursts of current. But if I'm confident if I left this on long enough, we'd be down in the nanoamps. So it's pretty much zero. I'll rate this down as, let's say, an average of 3 microamps, 2 microamps. Let's go. So that's what it's sitting at right now. So I'll discharge this, and we'll put the next cap on. Next up is our solid polymer, and let's turn this one up and see how this one works. Let me get the timer started. And I'll bring you back in 10 minutes. Okay, 10 minutes with the solid polymer cap. And this journey was a lot smoother. The needle didn't bounce around as much as the first one did. It came down a lot smoother, but right now it's kind of doing a breathing thing where the current goes up to about 2.5 microamps, and then it goes down to about 1 microamp. And it's slowly doing this up and down, up and down. I have a feeling it's gonna, well, we're at 10 minutes now, and it's resting right around 2 microamps or less. See, right now it's at 2 microamps. Then it's going to go down. I don't know if you can see that movement there. It's very slight now. It's starting to really settle out. So I'm going to give this one about a 1.5 microamps. Next up is the Chemet cap from DigiKey. We're going to test this one now. So let's turn up the current. Okay, get my timer set. Okay, it's dropping quite fast. Bring you back in 10 minutes again. Okay, after 10 minutes with the Chemet cap on full rated voltage, the meter is still jumping from between 2 and 4 microamps. You can see it's settled down now as soon as I turn the camera on, but it was coming up to almost 5. So it's still doing its forming thing. I'm going to give this one, there it goes. It went up. I'm going to give this one 3 microamps, just because it is still making quite a few bounces. Okay, next up we have our Nichicon audio grade cap, and we will get this one started. Let's turn this one up. Start my timer. Okay, I'll give this one, bring you back in 10 minutes. So we're coming up to the 10-minute mark here, and this one seems to be the best out of the bunch. This one's hanging around the 1 microamp mark. Sometimes it dips to 0. Sometimes it rises up to about 4 microamps. See, right now it's kind of going up and down. It's right around 2.5. Then it goes down to almost 0, and then it comes back up again, 2.5. So this one seems to be doing the best here out of all of them. I think I'm going to give this one a rating of 1 microamp. Okay, here we go. We got our tired old Elna, and we're going to see how this one performs. So let's turn this one on. Start my timer. And we'll see how this one does. Okay, we're coming up to 10 minutes now. This one's not doing so good. This one's fluctuating between about 8 and 10 microamps. You see, going up and down there. It goes down to about 6, and then it goes back up. It's hanging out around the 9 mark there. Just trying to get a sense of where it's spending the bulk of its time. It seems like it's right around 8. Regardless, it's not a very good cap if it's that much higher than the others. So we're going to give it a rating of 8. Okay, I took the data, put it on this sheet. I hope you can read it. I tried to make the font fairly large, but there's a lot of information here. I wanted to get it on screen. So we have our comparison data. Now, depends on what you want to use your capacitor for. Each capacitor has different applications. This is an audio capacitor. This is a capacitor that's built for switch mode power supplies. Here's just a general purpose cap. Here's a solid polymer high performance cap, and here's an Elna from the blast from the past. So if you start looking at the data, I measured test frequency first at 120 Hertz, and then I did it again at 10 kilohertz to see the difference. After I did the 10 kilohertz test, I did the leakage current test on each cap, and then I performed the 120 Hertz test again to see what changed after having sit on full rated voltage for 10 minutes. And you'll see there's a little bit of a change here, but not much. So all these caps are rated at 105C except for this one, and this is your age in the capacitor. The only one I don't know the age of is the solid polymer. I don't know there's no date code on this. If there is, I can't read it. But if you're looking for just a good performing capacitor, looks like out of all this data, it looks like the solid polymer is the best choice. It has good tolerance with regards to the value. It was only out by less than 2%. It has the best ESR of all of them, and it had the best dissipation factor. Okay, but we can't use solid polymer caps in every application. They're only intended basically for power supplies and filtering of power. They're not good for coupling. You can't use them in frequency circuits. They can be damaged, and they can create leakage current if they are overheated. And they have an undesirable failure mode where they go short circuit. So these are best left for power supplies. Now the next runner-up would be the Nichicon KA series. These are the next one that was closest with value. Okay. Now this would be a good thing. Accuracy and value is a good thing if you're in audio circuits and you want to have, you know, balance between your left and right channel. You want to have the same cap value in the circuit for the right and left. This would be your choice, Nichicon, and you could actually test these and make sure that they're within spec. It was only 1.4% out of tolerance. It had a good dissipation factor, and it had a good ESR. So this is a good choice for audio, and it's a good choice for a lot of general purpose stuff too. The Wyman cap, these are my favorites. Didn't perform as good as I was hoping, but they're still good performers. You were 9% out on value, and our ESRs was starting to get up there. It's twice as much as the solid polymer, but it's still pretty good. It's still doing better than our Chemet cap and our Nichicon cap. So this is a good performer as far as ESR goes. Now the one that really surprised me was this Chemet cap. It didn't really shine out above the rest. It actually underperformed. I don't know if it's because it's actually about 4 years old, this cap, but it was the farthest out on tolerance, and it had the highest ESR of 0.32 ohms. And you know, things don't get better when you increase frequency. So if you look at the difference between the 120 hertz chart and the 10 kilohertz chart, you can see the difference between them. You want to pause it and let me zoom in a bit. There, hopefully you can read that a little better. So if you want, you can pause this and you can read the difference between these two frequencies. And you know, electrolytics aren't happy at higher frequencies. They like working at low frequencies. So yeah, as the frequency goes up, things start falling off. This Elna cap really surprised me. It has some really good specs for being like a 50-year-old cap. 234 microfarad, it was 6.4% out of tolerance. Had a good measured ESR, which is one of the best, actually. And I have a feeling that's because of its size and its construction. It probably has a large surface area inside, which amounts to a low ESR. Dissipation factor is also good. And yeah, where it failed was on the leakage current. This is where it failed. These four caps, this is pretty normal and typical. This is what you'd expect. And then the Elna cap, you know, being so old, it's got high leakage. Now another thing I tried is testing again after leakage current, because these four were all brand new caps, right? Brand new caps, never been electrified before. So I wanted to see if there was a difference between before and after the leakage current test, and really not much of a change. Actually, things got a little bit worse, to tell you the truth. Let's see here. Where did I see this? ESR went down, went down, went down, went down, went down. ESR went down on all four of these by a slight amount. Dissipation factor went up a little bit, very slight amount on all these four. Tolerance, well, some changes, not bad. Interestingly enough, the before and after for the Elna cap were identical. Okay, they're pretty much identical readings. So you can tell this cap has already been formed and used, and having put 50 volts on it for 10 minutes made no change in its specs. So it's kind of an interesting test. I don't know if you're wanting to use caps for audio. If you have power supply, I would go with the solid polymers. Although they do have problems, you got to make sure you have proper fusing in your circuits, because they will short circuit if they are overheated or reverse polarity. They do not handle reverse polarity at all, so you must avoid having reverse polarity on these. So that's the reason they're not used for coupling caps. They're not used for timing caps. They're not used for, what was the other one? But they're great for bypass caps, right? And for coupling caps in audio circuits, I would go with these. These are pretty good. And just for general purpose, non-critical, I would go with Kemet. Everything else, this is general purpose too, but it's got a little more performance than the Kemet. It's got higher performance. It's supposed to have a higher life. That's why I like these, because they have long life. And then it was kind of interesting to see how this Elna held up. I wish I had more old caps to test in comparison, because I know Nippon Chemcon and older Nichicons and old Panasonics, they all behave differently as they age. So I might just do that. I might collect up some old caps from repairs, and we'll test them as see how they aged. So I don't know if this helps you out at all, and hope you found it interesting. I kind of found it interesting putting it together. So thanks for watching. Take care, and we'll see you on the next one.